Now let us see the chemical reactions of aldehydes and ketones. The first and the most important reaction of the aldehydes ketones is their nucleophilic addition reactions. Remember, these are their characteristic reactions. Let us first see the mechanism of the reaction. See, we know that if we are having any aldehyde, or a ketone, let me name the groups as A or B. We know that this bond is already polar. Now that is why the moment the nucleophile comes in contact with these type of molecular species, it shows the nucleophilic attack or nucleophilic addition attack on the carbonyl carbon, which is already electron deficient, due to which the shifting of the pi bond to the oxygen takes place. Now oxygen was already having 2 lone pairs, and because of the shifting it will acquire what? A third pair. The most important thing before moving ahead to note is that this carbonyl carbon is sp2 hybridized, and that is why this molecular species is trigonal planar. Now since this is trigonal planar, the nucleophilic attack can take place from both the sides. This is always therefore going to give us what? Racemic mixture if the reactant is optically active. And then what happens is we get a sort of a product which is actually like this, which will be tetrahedral. Now this intermediate acquires any H plus or any electrophile, it attracts it, and at the end what we get is A, B, nucleophile, O and electrophile. So this is what is the product, the additional product called adduct is formed. So this is the mechanism of the addition, the nucleophilic addition reaction we have. Now let us discuss the reactivity among the aldehydes and ketones towards this nucleophilic addition reaction. Now let us discuss their reactivity. See, if we compare the reactivity, we can easily find this is the order of the reactivity. Let me draw it here in between. So this is the order, this is the decreasing order of reactivity towards nucleophilic addition reaction. This is a normal aldehyde, formaldehyde, methanol. This is any higher aldehyde, and this is a ketone. Now why the order is like this, why the ketones are least reactive? The reason is because what happens is there are 2 reasons. The first is the plus I effect. Remember, we are having plus I effect only from one side in case of these higher aldehydes, and we are having plus I from 2 sides. Now due to this plus I, this electron deficiency of this carbon gets neutralized to maximum extent in case of ketones, to little extent in case of higher aldehydes, and to no extent in case of methanol, because it is not having any methyl group or alkyl group attached to the carbonyl carbon. That is why this becomes most reactive. The second is the steric hindrance. Now the steric hindrance is maximum in case of ketones because of these bulky alkyl groups. So the attack of the nucleophile will be very, very difficult. Whereas in case of methanol it becomes very easy because we have only the protons, the H hydrogen. That is why, because of these factors, we realize that the methanol is the most reactive aldehyde we have among all the aldehydes and ketones. Then we have higher aldehydes, and then we have ketones. Now let us see the examples of the nucleophilic addition reaction. Now let us see the examples of nucleophilic addition reaction. The first is addition of HCN. That's called hydrogen cyanide. See, in this what we can take is, if we are having any aldehyde or a ketone, I am writing down R or H, it means it can be a ketone or it can be an aldehyde. And if we are adding HCN to this, we know that the addition will be like this. The CN will come out as CN minus as a nucleophile. It will attack on the electron deficient carbon, which will lead to the shifting of the pi bond to the oxygen, which will attract this H plus. So ultimately what we get is this compound OH and CN. Now the compound becomes optically active, but we will get racemic mixture because attack takes place from both the sides. The compound formed is called cyanohydrin. So this is practically the first example of seeing the addition of HCN, which gives us what? Cyanohydrin or alpha hydroxynitriles. Alpha hydroxynitriles. So that is what their IUPAC name will be. So that's the first example. Let us take now the second example of the nucleophilic addition reactions, and it is the addition of sodium hydrogen sulfide or sodium bisulfide. Now if we have any aldehyde or a ketone and we react this with sodium bisulfide, addition takes place like this, which will shift the double bond towards oxygen, which will attract sodium. So what we get as the product is your ONA plus minus and OSO2H. So basically what we get is sulfonic acid. Now this and this is a base. So it shows what? Self-neutralization. It shows self-neutralization, and what we get is your OH plus SO3Na. So what we get is sodium salt of alpha hydroxy alkyl sulfonates. That's a sodium salt of the sulfides, alkyl sulfides with hydroxy group at the alpha position, and that is what we say about this one. This compound appears as a salt and it is easily being crystallized out, and the best part is this: when this is again heated with HCl, what we get is the aldehyde or the ketone back plus NaCl plus SO2 plus H2O. Now the most important thing is this is that is why we are getting the aldehyde of the ketone which were taken initially back, and that is why this reaction is used used for the purification of the aldehydes in ketone, because this aldehyde ketone formed by the reaction of decomposition of this salt is the pure aldehyde in the ketone which we have got. That is why this reaction with bisulfide is mainly used for the purification of aldehydes in ketones. Let us see the third example, which involves addition of Grignard reagent. This we have already done in case of the preparation of alcohols in the last chapter, that if we have, suppose, formaldehyde, methyl magnesium bromide first, followed by hydrolysis in acidic medium, is going to give us what? Primary alcohol plus MgOH-Br. If we are having, this was methanol. If we are having any higher aldehyde and we react this with methyl magnesium bromide followed by hydrolysis, we will be getting what? Secondary alcohol plus MgOH-Br. And if we have, this was ethanol, and if we have a ketone like propanol reacted with methyl magnesium bromide followed by hydrolysis, this is going to give us tertiary alcohol. So this is how we can get different types of alcohols by the nucleophilic addition of the Grignard reagent on the different aldehydes and ketones. Now let us see the fourth addition, which is the addition of alcohols. See, if we have any aldehyde and we add any alcohol R dash OH, it shows nucleophilic addition, and what we get in the first stage is OH plus OR dash. This is called hemiacetal. This on further reaction with alcohol molecule is going to give us what? OR dash OR dash H, which is called acetal. So acetal is the compounds which are having actually two ether groups on the same carbon, and we get acetal at the end if we continue to react this with the hemiacetal form with the another alcohol molecule. Similarly, if we are having a ketone here, it is going to give us what? Hemiketal, or like, let me give you an example. Like if we are having, suppose, a ketone and we are reacting this with R dash OH alcohol, it will first give us OH and OR dash. This will be called hemiketal, and this on reaction with another alcohol molecule, OR dash R, that's called ketal. So we are having, again, since it is obtained from a ketone, we will call it a ketal, but it is a ketal. Why? Because it is having two ether groups on the same carbon atom. That's why we call it a ketal. But yes, we can use, in place of this, let me give you an example, like we can use glycol here. So if glycol is used with ketone, what we get is the HH goes out from here and the O remains here. So what we get is this compound, the cyclic ethers, which are called cyclic ketal. So this is how we can get, yes, cyclic ketals, or if we have taken the aldehyde, we would have got the cyclic acetal. So this is how we have the addition of the alcohols on the different aldehydes and ketones. The next example of the nucleophilic addition reactions is the addition of ammonia and its derivatives. See, if we have any alkyl halide aldehyde or a ketone like this one, and if we react it with ammonia, what happens is, first this intermediate is formed, which on heating gives us what? Double bonded NH. So the addition of ammonia results in the formation of imine. Similarly, the derivatives of ammonia are also added like this, which is an example of a nucleophilic addition reaction, followed by elimination of water takes place. So it's minus water, and what happens is, what we get is corresponding ammonia derivative compounds are formed. Chemically, basically all the compounds formed will be amines or some other one which will be named as the derivatives will be taken up. Another important thing is that this addition reaction takes place usually in the slightly acidic medium of pH 3 to 5. Let us see if we have any alkyl amine. If we have, suppose, like this is the aldehyde or a ketone we have, and we have a primary amine R dash. Now its addition will give us what? RCR, RH, OH, NHR dash. This with the loss of water will give us this compound. Now this is called substituted imine, which is also called Skiff's base, which are used as a reagents to check the presence of aldehyde or ketone groups. Let us see now the other ammonia derivatives. The first one in the list is this hydrazine. The addition of this hydrazine, which is one of the ammonia derivatives, at a pH of 3 to 5 leads to what? The formation of the water goes out like this. So I am putting up minus water here. It is going to give you NNH2. This compound formed is called hydrazone or N-amine imine. N-amino imine, because N-amino group is a substitution on the imine group. But it is in usual nomenclature it's called hydrazone. So hydrazine with aldehydes or ketones gives us hydrazone. Let us see now the addition of the second ammonia derivative. We say if we have any aldehyde oblique a ketone, whatever we can take, if we react this with NH2OH, which is called hydroxyl amine at a pH of 3 to 5, this results in the formation of N-hydroxyimine, which is called oxime, which are again orange-red compounds. Please remember, imines, the substituted imines, and all these ammonia derivatives we'll be doing now, they all are orange-red colored compounds. They are often used as orange-red dyes, and chemically they are imines basically. Now let us see. So what we realize is by the addition of this hydroxylamine is it always gives us the organic function groups or compounds formed called oximes. Now let us see the addition of other ammonia derivatives. If we have any aldehyde or a ketone group like this, and the next ammonia derivative we have is called phenyl hydrazine. The reaction takes place at a pH of 3 to 5. What we get is we get phenyl hydrazone, and the water goes out like this. So every time nucleophilic addition is taking place, these ammonia derivatives are very good nucleophiles, and the elimination of water leads to the formation of what? These compounds chemically are imines. So we get, with the addition of phenyl hydrazine, we get phenyl hydrazone. Now let us see the next one. The next ammonia derivative is this compound, which is called 2,4-dinitrophenyl hydrazine. This at a pH of 3 to 5 leads to the formation of this compound called 2,4-dinitrophenyl hydrazone with the elimination of water. So this is what we get. So what we need to know is this 2,4-DNP gives us 2,4-dinitrophenyl hydrazone on nucleophilic addition to aldehydes and ketones. The last ammonia derivative is is NH2 NH C double bond O NH2. This is called semicarbazide. Now this is an amide group attached to the hydrazine. Remember, the attack of the semicarbazide takes place from the nitrogen of the hydrazine group and not from the nitrogen of the amide group. The reason being it is involved in resonance with this carbonyl group. So this attack takes place and the water goes out like this. The addition takes place at a pH of 3 to 5. So minus water. This results in the formation of NH C double bond O NH2. This is compound formed is called semicarbazone. So this is how we can have the addition of the ammonia derivatives also, which is following a nucleophilic addition reaction mechanism on the aldehydes and ketones. Now let us see the reduction reactions of aldehydes and ketones. Now they are of two types. First is reduction to alcohols. Now this can be done by using LiLH4 or NaBH4. This we have seen already in the preparation of the alcohols. If we have any aldehyde, this on reaction with NaBH4 or LiLH4 gives us what? The corresponding primary alcohol. So aldehydes gives us primary alcohol, and if we have ketones, they on reaction with LiLH4 or NaBH4 gives us secondary alcohols. So this is a very good reduction method of aldehydes and ketones to the alcohols, and in this what we find is aldehydes gives us primary alcohol and ketones gives us secondary alcohol, and we know that these two are the best reagent, and out of these lithium aluminum hydride is the better one. The second reduction method is involving the reduction of aldehydes and ketones to the corresponding alkanes. So reduction to alkanes. Now this reduction is done by first is Clemenson's reduction. In this what we do is, if we have any aldehyde or a ketone, that these aldehydes and ketones on reaction with zinc amalgam in presence of HCl results in the formation of corresponding alkane is formed in this reaction. So corresponding alkane is formed in this system and along with the elimination of water. And what we find is, if we have a ketone like this, suppose this is the ketone we have, so with zinc amalgam HCl, this gives us corresponding alkane is formed. So Clemenson reduction is very simple. It's catalytic reduction of any aldehydes and ketones to corresponding alkanes by using what? Zinc amalgam alloy in presence of HCl. The second method of reducing the aldehydes and ketones to the corresponding alkanes is called Wolff-Kishner reduction. In this what happens is, the aldehyde or the ketone taken, let us take first aldehyde, is converted into hydrazone, and this hydrazone is then heated with KOH and glycol. This results in the elimination of this nitrogen or in between nitrogen, and this gives us what? Corresponding alkane. So we have taken here aldehyde, so we get alkane here in this case. If we are having a ketone, like let me give you example, if we are having propanol, this on reduction by using first hydrazine followed by heating with KOH and glycol gives us corresponding what? Propane. So this is what is reduction to hydrocarbon is. Now let us see the third type of reactions of aldehyde and ketones, which are called their oxidation reactions. See, let us see their first simple oxidation involving KMnO4 basic medium or KMnO4 acidic medium. See, any aldehyde on oxidation by these reagents gives us corresponding carboxylic acids. The example we can take is acetaldehyde on oxidation with KMnO4 acidic medium gets easily converted to acetic or ethanoic acid. Now let us see the oxidation of ketones. See, if we have a ketone, like let us take the example of we have acetone. Now what happens is, if we are doing its oxidation by these oxidizing agents, remember, since this is not having any CH bond associated with this carbonyl carbon, definitely one thing is involved, the breaking of the CC bond. Now in case of the symmetrical ketones, that doesn't make any difference whether this CC bond breaks or this CC bond breaks, because that is going to give you almost the same type of products, that we will be getting what? One product of 2 carbon and another product of 3 carbon. What you need to understand is that both these products gets oxidized to their corresponding carboxylic acids. So we will get the 2 carbon acid, acetic acid, and a 1 carbon acid, formic acid. That's the most interesting thing we are having. If we are having unsymmetrical ketones, like this one, we have 2-pentanone. In this case, Popoff's rule is followed, which states that the cleavage of that CC bond will take place, which will keep the carbonyl group with the smaller group. This will keep the carbonyl group with the smaller carbon chain, called smaller carbon group. So this in this ketone, the cleavage will not take place from this side, it will take from this side, so that the carbonyl group goes with the smaller chain. So that is why we will be getting one 3-carbon product and a 2-carbon product. 3-carbon product is going to give us what? Propanoic acid, and 2-carbon product will be going to give us acetic acid. So this is what we have, is the oxidation of aldehydes and ketones. And let us see now, we can have oxidation by some mild oxidizing agents also, like toluenes and ferrings. Let us see first the toluenes reagent oxidation reaction. Now let us see the oxidation of aldehyde and ketones by mild oxidizing agents. Let us take the example of the first one, which is called toluenes reagent. See, chemically toluenes reagent is this diamine silver 1 hydroxide. This is called toluenes reagent. It is formed when silver nitrate is treated with any base, which give rise to the formation of brown colored precipitates of silver hydroxide, which in aqueous ammonium hydroxide solution dissolves and forms this compound, which is called diamine silver 1 hydroxide. This is what is your toluenes reagent is. So when any aldehyde is actually heated with this toluenes reagent, what happens is the silver gets reduced and it oxidizes the aldehyde to corresponding carboxylic acid, and that silver which gets reduced forms a silver mirror at the bottom of the test tube, and that is why this test is also called silver mirror test. Let me describe it like this. If this is the aldehyde and this is the tolerance reagent we have, in basic medium, when it is heated, what it forms is, it oxidizes it into this corresponding carboxylic acid, itself gets reduced to silver, which forms silver mirror, and it forms ammonia plus water. So this is what is the reaction is, and this formation of the silver mirror leads to the identification that the compound which we are having is having what? The aldehyde group. Out of the carbonyl group, it is aldehyde group. Now this test is not shown by the ketone, the reason being this diamine silver 1 hydroxide cannot oxidize ketones as it cannot break the CC bond. So ketones doesn't give this tolerance reagent test. Now let us see the next one, which is called failing solution test. The next mild oxidizing agent is the failing solution or failing reagent, and its reaction is called failing solution test. Basically, failing reagent is a mixture of failings A and failings B. Failings A is ammoniacal solution of copper sulfate, and failings B is ammoniacal solution of sodium potassium tartrate. Now in this, chemically, it is the cupric ions which are acting as an oxidizing agent in basic medium. Now what we need to understand is this is a weaker oxidizing agent than toluenes, the reason being the oxidizing power of the cupric ions is less than silver because its reduction potential is less than the silver, Ag+. So that is why this failing reagent is not able to oxidize what aromatic aldehydes. It is only able to oxidize aliphatic aldehydes to corresponding carboxylic acids, and it fails on aromatic aldehydes as well as on ketones. And what is the reaction is? When we take any aldehyde, it has to be what? Aliphatic, and it is reacted with this failing reagent, which is cupric ions in presence of basic medium. It gets oxidized to corresponding carboxylic acid, and the cupric ions gets reduced to what? Red precipitates of cuprous oxide plus water. So the formation of this red precipitates of cuprous oxide is an indication that the compound is having what? Aldehyde group and not the ketone group. And remember, even if we have an aromatic aldehyde group like benzaldehyde, and if we react this with cupric ions in basic medium, we need to again, we have to do what? We have to mix the compound with the failing reagent, and we have to heat it on a water bath so that this red precipitates are formed. If we do this with the aromatic aldehydes, no reaction takes place, no red precipitates, whereas if we have reacted this one with your tolerance reagent, which is diamine silver 1 hydroxide, what would have happened is we have got benzoic acid and the silver would have been formed, which gives us silver mirror test. So this is how we can distinguish the aromatic aldehydes from the normal aliphatic aldehydes also. The third oxidation reaction of the aldehydes and ketones is their haloform oxidation or haloform reaction, which is mainly shown by methyl ketones, which are having what? 3 alpha hydrogens. Those ketones which are having 3 alpha hydrogens, or by those aldehydes which are having 3 alpha hydrogens, and in this category of aldehydes we have only the ethanol of this type. Otherwise, that is why we say this reaction is mainly shown by the methyl ketones. Now let us see what is this reaction is. Like what we do is, if we have suppose this kind of a ketone which is having a methyl ketone, an alpha carbon with 3 hydrogen atoms, and we react this with NaOX. Remember, X can be your chlorine, your bromine and your iodine. Remember, if we are having NaOCl, it's called sodium hypochlorite. NaOBr is called sodium hypobromite, and NaOI is called sodium hypoiodite. Now remember, this is going to give us what? Chloroform. This is going to give us bromoform, and this is going to give us iodoform. So they all gives the similar type of products together, which are commonly called haloform. And what happens is rest of the part of the carbon of the ketone gets converted to its carboxylic acid, and this carbon gets changed to the haloform. So let us see how this happens is it gets converted into RC double bond ONA, and what we get is CHX3. This is what is the oxidation reaction is. So if we have CH3 C double bond O CH3 propanon, and if we take NaOCl, sodium hypochlorite, what we get is CH3 C double bond OONA, sodium acetate. So acid with one carbon less is formed, and the one carbon which gets lost gets converted into what? Chloroform or bromoform or for iodoform. When the same acetone is reacted with NaOI, this is going to give us the same sodium acetate, but this will give us other than the chloroform, sodium acetate will give us what? Iodoform, which will come out as a yellow precipitates, and that is why this reaction is used to distinguish between the different aldehydes and ketones, specifically ketones from those which are not having the carbon atoms with the 3 alpha hydrogens. So that's why we can use it as a distinguishing reaction also. Now let us see the fourth category of reactions, which are called reactions due to alpha hydrogen. What you need to understand is that the alpha hydrogen of aldehydes and ketones are acidic. They are acidic in nature. Why? Because of tautomerism. Let me give an idea. Like if we are having this ethanol, we know that this will involve what? Attract the pi electrons towards itself, so that this carbon becomes electron deficient. It will pull the electrons from this alpha carbon. So what it will do is it will shift its one pair which it is sharing with the hydrogen towards this carbon, and this oxygen therefore will attract this hydrogen toward itself. This leads to the formation of what? CH2COH and this H. So enol is formed. We know that so all aldehydes and ketones show this tautomerism, and as a result this hydrogen usually comes out as H plus and is readily available. That is why the moment we provide them a basic medium, this H plus goes out, and this leads to the formation of a nucleophile, and that is why we have a very different category of reactions which are shown by these aldehydes and ketones. Now let us see this one, and the first in the category is your aldol condensation. It's called aldol condensation. Now what is this reaction is? It is a reaction which is shown by the aldehydes and ketones which are having what? Alpha hydrogen, which when exposed to what? Basic medium, two of their molecules condenses to form beta hydroxy aldehydes or ketones. So what we get is when two of these molecules will combine to form beta hydroxy aldehyde or a ketone, like this compound. This is beta hydroxy. There is a hydroxy group at the beta carbon, this is alpha and this is beta. That's why it's called beta hydroxy aldehyde or ketone form. And what we say in this case is that, and this compound on heating will lead to what? Dehydration, a loss of water takes place, and what we get is CH3CH double bond CHCHO compound formed is called crotonaldehyde. Alpha beta unsaturated aldehyde or ketone. So it's a condensation reaction in which what is happening is the two molecules are combining to form what? Beta hydroxy aldehyde or ketone. Let us see the mechanism of this reaction, how it takes place. Basically what happens is, we know that the carbonyl group is showing tautomerism. So when a basic medium is provided, it moves out with the H plus or acidic hydrogen of the aldehyde, leading to the formation of a nucleophile, which itself is resonatingly stabilized, Now this nucleophile attacks on the other carbonyl group, leading to the formation of this compound, which from water takes up one H and leads to the formation of, there will be H here also, an OH group, CH double bond O plus OH minus. So this is how beta hydroxy, sorry, I have left out this hydrogen SCH2 here in between. This will be CH2, CHO. So what we get in fact is this compound, and beta hydroxy aldehyde or ketone is formed by this. Now this mechanism suggests us that we are using only the alpha hydrogen of one of the aldehyde group, aldehyde molecule. The other molecules alpha hydrogens are not at all used. This gave us the idea that yes, we can take two different aldehydes and ketones also for this reaction, and that is what leads to for the next reaction, which is called cross aldol condensation. But let us see first this reaction with some other examples. If we have this ketone in basic medium, two of its molecules condenses to form this beta hydroxy ketone. So this is what are the products we get out of this. If we are having, suppose, acetophenone, it is having this alpha 1, what will happen is the product formed will be this ketone. So this is how the different aldol products are formed. Now let us see the next reaction, which is called cross aldol condensation. Cross aldol condensation. In cross aldol condensation, we take two different aldehydes or ketone molecular species and we treat them with the basic medium. What is important condition to note is that one of them must be having an alpha hydrogen and other may or may not can have. So let us take first those examples in which what we have is one molecule with alpha hydrogen and other one without alpha hydrogen. So this is having alpha hydrogen, this is having no alpha hydrogen. So we have seen the mechanism. The one which is having alpha hydrogen or whose alpha hydrogen is being used gets converted into nucleophile. In this case, it is the only one which gets what is having an alpha hydrogen. So it's only the alpha hydrogen will be used and it will be converted into a nucleophile, which will be doing an attack on this formaldehyde molecule. So if we name this reactant as 1 and this as 2, what we will get is we will get two products out of this. One is the attack of the 2 on the 1, and other one is the attack of the 2 on the 2 also, the same type of molecules. That is why this leads to the formation of two type of molecular species. One is called cross product, another is called self product. Let me tell you like this. If this attacks on this one, its carbonyl group gets converted into an OH and its H gets shifted, alpha H gets shifted to this OH. So the product formed is this. This is called 2 on 1 and it's called cross product. And the other one will be the attack of this on the same one, which will be CH3CHOH, CH2CHO. This is called 2 on 2 and this is called self product. Now out of these, definitely this will be your major one, because remember, out of those cross and self products, the one which is having the attack of the more substituted one on a lesser substituted one will be the major one. So this is having more substitution, so more steric hindrance, but it will be a better nucleophile, and this one is having what, less steric hindrance, less substitutions. Therefore, the more attack can take place on this. So out of the attack of this on this or this on the same type of molecules, this cross one will be the major product. Now let us see some other example, next example, in which we will be having what, both the molecules will be having what, the alpha hydrogens. Let me take you the example of this type of molecular species like this one. Now such type of molecules, in this such type of molecular species, both are having what, alpha hydrogens. Now what can happen? 4 products are formed. Yes, 4 products are formed. The one will be the attack of this on this one, other one will be the attack of 1 on 2, the third will be the 2 will be the self ones, 1 on 1 and 2 on 2. So let us first draw the cross products. The attack of 2 on 1 will be CH3, CHOH, CH2, C double bond O, CH3. This is called the attack of 2 on 1. Then we can have 1 on 2. So 1 on 2 will convert this into OH, CH3, CH2, CHO. This is called 1 on 2. And then these are the 2 cross ones we are having. And then let us see the self one. The self one of 1 on 1 will be like this. This is 1 on 1, whereas this will be your this will be called 2 on 2. So these 2 are your self products. So this is how we have cross aldol condensation. The next reaction of the aldehydes and ketones is called Cannizzaro reaction. In this Cannizzaro reaction, remember, it is only shown by aldehydes which are not having any alpha hydrogen. So remember, the condition is it is only shown by aldehydes with no alpha hydrogen. That's most important. Then what we find in this case is, now when such type of aldehydes, like let me give you example of methanol, on reaction with basic medium, strong basic medium, concentrated NaOH, shows disproportionate reaction to form what? One oxidized product, another reduced product. The oxidized product of an aldehyde is, we know, is the carboxylic acid, whose in basic medium sodium salt is formed, and reduced product of aldehyde will be the alcohol. So what we get is methanol. So one oxidized product, another reduced product is formed. So what we get is sodium formate or methanoate, and what we get is methanol. So this is what is yours called Cannizzaro reaction. If we have benzaldehyde, which is not having any alpha hydrogen, this was not also having no alpha hydrogen, no alpha hydrogen. This is your compound is called benzaldehyde. On reaction with strong basic medium, it is going to give us what? A one oxidized product, which is your sodium benzoate, and one reduced product, which is yours called benzyl alcohol. So this is what is called is Cannizzaro reaction. The next reaction of the aldehydes and ketones is their electrophilic substitution reactions. The aromatic aldehydes and ketones, remember, due to this carbonyl group, whether right IR or H, they are so from this resonating structure, this becomes very clear that these aldehydes and ketone groups and aromatic aldehydes and ketones, of course, due to their minus R effect, are what called ring deactivating groups and are meta-directing for their electrophilic substitution, because ortho, para and ortho places will get positive charge. So, electrophilic substitution in these cases takes place with difficulty, and that too at meta position. Let me write it down for you. If we have this benzaldehyde and we want to do nitration, we have to take nitric acid and sulfuric acid, nitrating mixture, that is going to give us meta-nitrobenzaldehyde. And if we want to take chlorine, we will take chlorine in AlCl3, that is going to give us metachlorobenzaldehyde. So this is how we can have what? Electrophilic substitution reactions on these aldehydes and ketones. Now what you need to know is that these aldehydes and ketones are very useful in our day-to-day life also. As I have told you, the higher aldehydes and ketones are having very pleasant smell, so they are very widely used in the preparation of their different perfumes, deos, etc. And as well as these are very important organic solvents. They are used in the preparation of a number of compounds, different organic compounds, and that is why they have a lot of their industrial applications also.